Let's look at a version of our interpreter that uses garbage collection so that interp and continue don't run out of memory. It starts out the same as before. We have an exp data type that we parse into, but then the exp conceptual data type that represents compiled code in memory, and values with their tags 15 and 16 just as before. We still have continuation records with all of their tags. We have environments with the tag 17, but we also have this new thing, a tag for moved objects, which is 99. So this is not an object that the interpreter cares about. It's just for the garbage collector. It actually refers to the forwarding pointer. So 99 is like a purple object that says we've already moved the object, and so inside now is just a forwarding pointer. So we'll see that more when we look at the garbage collector. The parser is the same as before. For the compiler, it needs to compile code into memory somewhere, but this is the same sort of allocator that we had before, but we're calling it code malloc instead of malloc. And so we're making 2K space for our code. We can have programs up to that size, but we'll be able to allocate more memory and release memory that is not code. So you can think of code memory as ROM, and compile is allocating all of the compiled code into that code space. Now we have the other memory though, and this is the garbage collected memory that is used for runtime interp. So we're going to have 256 slots in our memory, which for a two-space collector we'll divide in half, so each of those spaces is going to be 128. So I'll just make space 1 and space 2, and we'll start out allocating into space 1. I also need an extra little sentinel that I'll call empty memory, and that'll help us detect that when we're trying to garbage collect and we run out of memory during the garbage collector, in case we really have just run out of memory and there's too much going on in the program. The garbage collector is going to be triggered when we try to allocate. So we have inc pointer like we had before, which is the last step of allocation. It bumps the allocation pointer right here. But now inc pointer is going to do one more thing. It's going to look ahead and say, what if we try to allocate next time, will be out of space? It just turns out to be easiest to phrase things this way, to look ahead one allocation. It turns out we never need anything bigger than 5, so that's why there's a 5 here. So if we were run out of space and next time we try to allocate, then what we do is we remember what we were going to return this time, and then perform a garbage collection, and GC is responsible at the end for returning that result register. If in the process of running a GC though, we end up back here and we still ran out of memory, then that empty memory sentinel will tell us that we're in that kind of case, and then we really are. Just can't keep running the program. Malloc 1, malloc 2, malloc 3, those look all pretty much the same way they did before. And then we have the garbage collector, which was triggered by inc pointer, and we'll come back to that in just a moment. But first, let's go down to interp and continue, just to see that they look the same as before. The main difference, the only difference really, is where we used to use ref always. Now we use code ref when we're looking inside of the expression register. And when we're not looking inside of the expression register, like when we look in kreg, that's a continuation record that's allocated at runtime. We just use regular ref there. So again, all the same aside from some of the refs turns into code refs, the places that we're looking at expressions. But now let's go look at how the garbage collector works. So the garbage collector starts out by printing that it's a garbage collection, just for information for us so we can see when the GC happens. And then the first thing it's going to do is swap to space and from space. That is, it'll remember the current memory is from memory, and then put the other space in place as memory, and we will start moving things into this new to space. Memory is always to space. So we set the allocation pointer to to space back to 0, and then the first thing the garbage collector does is it needs to paint all the register referenced objects gray. So the move function here is going to be the operation that paints an object gray, right? Because moving an object from old space to space, that's painting it gray. Okay. So we paint all 4 objects referenced by registers gray, including this result register that is here, just to remember the last thing we allocated. And then we set the pointer that is at the start of to space, so that we keep track of which objects have already gone from gray to black. Right? So we start out at 0 in the to space. And then we're going to go through our loop that is looking for gray objects, moving a gray object at a time, and so on. So update is that loop. If our update pointer register reaches the same as our allocation register, that is, our pointer sweeping across the gray objects eventually reaches the allocation pointer. That means there's no more gray objects. So we just set from memory back to empty memory now, because we're not working on the old space anymore. That's kind of the deallocation step there. And then return the result register that was waiting around when we started the garbage collection. But if there is a gray object, that means updated pointer reg points to it, we look at that object's tag. This pointer refers to an object that is gray, that it has already been copied, but it's gray, not black yet. We still have to look inside of it to find all the pointers, and that depends on the tag of that object. If the tag is 0 or 15, that's either a done k or an int v, then there are no pointers in that object, and so we're already done. So we just call this done function that will move the updated pointer forward and then keep going. If the tag is 1, 3, or 5, that means it's a record that has 2 runtime pointers. It's of size 3, and it has pointers in slots 2 and 3. So it turns out there are 3 different records that we have that have this particular shape. So we call moveDo on both of the offsets that have pointers, and then we are done with this size 3 object. We'll take a look at moveDo in a moment. We just have all the other tags are the different kinds of shapes. So it turns out there are like 5 or 6 different shapes that we have in our interpreter. moveDo is going to update one of the pointers inside of an object. So it's at the offset in our current object. We look at what's currently there, that is a pointer to another object. We want to make sure that other object is gray, so we call the move function. And move function's job is to copy it over if it's not already copied and return the new address that's in 2 space. And so we install that back into the object that we're updating. So moveDo calls move, but also installs the updated, the new address inside some other register. And then done here is incrementing that update pointer, and then just looping again by calling update to keep going looking for gray objects. So the remaining work to do is the move function, where we actually move objects from space to 2 space. Move receives an address, that is the address, the old address in from space, and we want to return the new address in 2 space. If the old address is pointing to an object that's already tagged 99, that means we're looking at a purple object, one that's already been copied over. It's already either black or gray, and we left a forwarding pointer behind just after the 99, so at offset 1 after that address in memory. Otherwise, we're looking at an object that's still white, and we need to actually copy it over. The way that we copy it over depends only on the size of the object. It turns out we don't care whether those pieces inside the object are pointers or not, so we just have different cases corresponding to the different sizes of objects that we have. And if it is a size 1 object, then we will call malloc1 to allocate a new object in 2 space. We'll give it the same tag it used to have and the same data it used to have, and so on. When malloc1 gives us an address back, then that's the address we want to return. It's also the address that we want to install as a forwarding pointer. So here we're installing it as a forwarding pointer in each of these different cases, and then the last thing we're going to do is return that forwarding pointer. But just before we return that forwarding pointer, which is the location, the new location of the object, we install the tag 99 to say that it has been moved. And so what will happen is that move keeps getting called by update, which keeps calling itself until it runs out of gray objects. And we can see this in action. We have all of our tests that we had before, but we're running in a much smaller heap now, only 128 bytes in each space. And so when I run it, we will see GCing print a bunch of times as the program runs, but all the tests pass.